Hello, this is the last short lesson of the 3 that I'm posting up. This is just an introduction to something called half-life, and we'll find out what half-life is a bit later on. But it's mainly about how long do radioactive materials live. In other words, how long are they radioactive for? Excuse me. Now, we've already seen that we can draw a radioactive nucleus like this, and then it spits out some particles. This would be 4 little particles, which is alpha. Here's another nucleus, which could get rid of 1 small particle, which is beta, or a different nucleus could send out some energy as a wave, and we know that that's gamma. Now, every time a radioactive nucleus gets rid of a bit of radiation, it becomes more stable. So a radioactive nucleus is unstable, and by getting rid of an alpha particle or a beta particle or a gamma wave, it becomes more stable, and eventually it will become nice and stable, and that's it. No more radioactivity will be released. So if I've got a large number of particles, and this is lots and lots, every one of these is lots and lots of protons and neutrons. So here's just one, and it looks like that. And we've zoomed out a little bit. I've got lots and lots of them that make up a material, and every single one of these nuclei is radioactive, and one by one they are going to give out radioactivity, an alpha or a beta or gamma, and the whole material is going to become more stable over a period of time. So the radioactivity decreases with time, because if every one of these is radioactive and I get rid of a couple because they've become more stable, then there's less radioactivity to be produced. And I'll get rid of a few more and there's less radioactivity being produced. And each one of these radioactive nuclei, when they decay, leaves behind a stable nucleus, and over a period of time all my little blue blobs, which are radioactive, will all convert themselves into green blobs, and there is no more radioactivity left in the material, and it's perfectly safe and it's perfectly stable. Okay, so this is what we need to do. We need to write down some information. That's just a little tiny brief introduction to what we're going to look at. We're going to write down some information, and I want you to copy this into your red jotter. So the nuclei, all those little nuclei together, they in a radioactive material, they're unstable. By the way, nuclei is just the plural of nucleus. So I've got one nucleus, or I might have thousands and thousands of nuclei or nucleuses. We don't say the word nucleuses, we use the word nuclei. As these nuclei decay, so the nuclei decay, and then you're left with a stable nucleus. So we've got less and less radioactive nuclei. Sorry, I can't spell here. Okay, so if I start off with 100 radioactive nuclei, after a period of time, there'd only be 90 left. And after another period of time, there'd only be 80 left, and so on. So you get less and less. The ones that stay behind are then not radioactive at all, and you've got less and less radioactive nuclei to decay over a period of time. So the activity of any sample decreases over time. Okay, so let's imagine, I hope you're going to get all that written down because I'm going to rub that out. Let's imagine that I have just one nucleus, and I want to see for how long is it going to hang about and be radioactive before it gives out either alpha, beta, or gamma. How long is it going to last for? How long is its life? How long is it going to be radioactive for? Now, this giving out alpha, beta, or gamma is what's known as a random process. You can't predict it. Okay, so the decay of a radioactive nucleus is random. We cannot predict when it's going to happen. Now, this is a bit like taking a coin. And if you take a coin, on one side there is the Queen's head, and the other side, it's not the Queen's tail, but we call it a tail. Okay, there's some other design on it. So a coin's got two sides. It's got a head side and it's got a tail side. And if you take that coin and you flick it up in the air and you toss it, you cannot predict whether you're going to get a heads or a tails. It's truly what's called random. And if you did the experiment over and over again, if you kept tossing a coin again and again and again, you could just try and guess. So this next one's going to be a head. No, it isn't. It's a tail. And it's random. It's a random event, and you cannot predict whether you're going to get a heads or a tail. So coin tossing is an example of a random event. So you can't predict whether you're going to get heads or tails. Any one coin, if you toss it, you cannot get it right. You cannot predict every time with 100% certainty of what it's going to do. But here's a thing. Say I had 100 coins and we tossed 100 coins. I bet you can work out roughly how many heads you'd get and how many tails you're going to get. If you've got a lot of coins, then roughly out of every 100, 50 of them, 50% would be heads and 50% would be tails. But you cannot predict what any one coin is going to do, whether it's going to be a heads or tails. So, however, So any one coin, you can't predict whether it's heads or tails, but lots and lots of them, you probably work out that 50% of them will be heads and 50% will be tails. And so that is predictable. We can actually turn a random event that we can't predict with just one coin. We can predict the behavior of lots and lots of coins if we keep tossing them and counting them up. Okay. So what's called the half-life is the time it takes for half of the nuclei to decay. So say we've got 100, I'm not going to draw 100, but say we've got 100, we can predict with radioactive materials how long it will take for half of them to decay. Okay, so these are two important learning points. The first one is that radioactivity gets less. And the second one is, what does half-life mean? Half-life means how long it takes for half of the radioactive nuclei to decay and to become stable. You'll need to get that written down. Now, if we do an experiment and we do some measuring and we do we record some results of this thing called half-life and how long it takes for half of the nuclei to decay, we'll end up with a very characteristic graph, something called a half-life curve. And what we've got here is something called the count rate. How many are in the game at the start? Okay, and then along the bottom we've got time, and we can record over a period of time. Perhaps we do this every 10 seconds. We'll take our Geiger counter connected to our measuring device, our Geiger counter connected to the actual counter that gives you the numbers of decays, and we'll stick it next to a lump of radioactivity. And this lump of radioactivity is going to decay. So right at the start of an experiment, you'd expect to get lots and lots of count rates, lots and lots of counts, which you could record, and you could write down a number and you could put it on a graph. A bit later on, say 10 seconds later, we'd expect some of those nuclei to have been decayed, and we're left with less. And then after another 10 seconds, we can record the count rate again, and so on and so on. And we would get this, what's called a decay curve. Eventually, that count rate would become zero. There would be no more radioactive nuclei left, and all the decays have taken place, and we're left with a stable material. Now, how long does that take? Well, every different radioactive element has its own time for half of the nuclei to decay. So with some radioactive materials, the time period is so long, we're talking about billions of years for half the radioactive material to decay. And there's a huge amount of radioactive material under the surface of the Earth, which is slowly decaying. And if the Earth is around long enough, and I'm talking like billions and billions of years, there would be no radioactivity left. There'd be no background radiation because there's just no radioactivity left. Every radioactive nucleus has decayed and it's become stable. Some materials have an extremely short, what's called half-life, how long it takes for half the nuclei to decay. And we're talking of fractions of a second. You might have all the radioactivity has disappeared in just about a second, for instance, and it's gone from being highly radioactive to not being radioactive at all. It's completely stable in a very, very short time. So I'm going to write that down. I hope that you're going to do this as well. I've got a GM tube. I've got my counter. And I've got my radioactive material. And we're just going to take count rates over a period of time. Now, it would help if we were going to do this in the classroom, it would help if we had a radioactive material that decayed in, say, 15 or 20 minutes. We don't want a material that's going to take billions of years to decay, because we're not going to be able to count it for billions of years. Neither do we want a material that's going to decay very, very quickly, because the experiment would be over and done with as soon as you've started. So if we're going to do this as an experiment in the classroom, we want something where we can actually observe the decay. It starts off quite active, and perhaps the time of the experiment might only be 20 minutes, and we could record what the count rate is, say every 10 seconds or every 30 seconds. And as the time goes on and on and on, 30 seconds, a minute, 1.5 minutes, 2.5 minutes, 3, the count rate would come down and down and down and down, and leave us with this thing called a decay curve, a radioactive decay curve. So you're getting an idea now of the sort of equipment that we need: a Geiger-Müller tube to take some counts, a counter to display the number, unless you're going to sit there and listen to the clicks and count them individually, some radioactive material, and you're going to want some sort of stock clock or timer, so you can take regular results, say every 30 seconds, record the count rate, and then plot this radioactive decay curve. Now, this is an experiment that we have to have some knowledge of, and so the way that I'm going to provide you with some more knowledge than just me talking about it and drawing some diagrams is there will be a link to a quick whiz through of an experiment, and you'll actually see this experiment take place with a radioactive material that is called protactinium. Protactinium is an element in the periodic table, and it's got a half-life that's probably round about 70 seconds or so. So every 70 seconds, you'd expect the count rate to have gone down by half. But what we could do is take a reading every 10 seconds or every 30 seconds and record that information and plot this graph. And this is what you're going to do. So I'm going to show you a little video. I'm going to provide a link where you can actually see this happening. We have got the same equipment in school, and we can do this, and I could get this out and we could do this ourselves, but you're not in school at the moment until after Easter for another 5 weeks. So I'm going to show you a video that shows you this equipment and how it works, and then I'm going to show you what's called a simulation of this taking place, and you will be able to record some results over a period of time, and you could plot a graph yourself. Now, plotting a graph is going to be a bit tricky because you haven't got any graph paper for now, but what I want to do is to get this idea of the experiment down in your books, to say how it would happen. I'm going to get you to watch the little video so you can actually see the equipment in use. I'm going to show you the simulation. There will be links, and I'm going to ask you to record the information in a table. There is a table in your course notes that's not filled in, and you're asked to watch the video and record the time and record the count rate in the table, and I'm going to get you to do that. The graph plotting, I think, will actually leave till later, probably until after Easter, but at least you can get the results. You can make the table. If you really fancy it, you could try plotting a graph using Google electronically. But what you really need to be able to do in any exam is take a set of results and plot a graph on a piece of graph paper and hand that in for marking. There's no electronic submission of graphs in exams, but it wouldn't harm you to have a go electronically if you thought you could do so. And you can do that using Google Sheets, where you record your table and then you get Google Sheets to actually plot the graph for you automatically. You don't have to put every little dot on and join up the dots with a nice smooth curve to get that. So there'll be more information about that very shortly. But for now, all I need you to do is write down this brief introduction to Half-Life. I hope you've got all those notes that I've written down. There have been a couple of boards worth. I want you to watch the video and I want you to watch the simulation, and I'm going to get you to record the count rate over a period of time in a table, and the table is already in your radiation course notes ready for you to fill in all the details. So you'll fill in the table and then we'll have a go at drawing the graph later on after Easter. I'm going to stop there and leave you to move on.